Okay, so I'm now going to really get started with the meat of the course. So we'll discuss some important concepts regarding Markov processes. Next lecture, we'll talk about Markov decision processes, and then we'll talk about reinforcement learning. So we're doing this gradually. So Markov processes are important in order to model environment dynamics. So here the idea is that we've got a reinforcement learning agent that's going to select actions as part of the environment, but this environment is evolving, right? So it will have some dynamics, and then so we're going to need to model this. And so for this, we're going to use stochastic processes. And those stochastic processes, we're going to make two important assumptions, the Markovian assumption and the stationary assumption. So that's what I'm going to cover for the rest of this lecture and in the next few slides. Okay, so as a quick recall, this is our abstract representation for reinforcement learning. And again, this essentially encodes a feedback loop where an agent executes an action, then the environment provides a state and a reward, then there's an action executed, state and a reward, and so on. So if we unroll the problem over time, right, so we unroll this loop, then what we would observe is that at a certain time step, the environment is in some state, then the agent executes an action, and then a reward is provided. Then there's going to be another state for the environment that results from the action taken. Then the agent will take a new action. There will be a new reward provided by the environment, and so on. Okay, so then this feedback loop leads to this sequence of state, action, reward, state, action, reward, state, action, reward. So this sequence, in general, is going to form a stochastic process, in part because there's going to be some uncertainty in the dynamics that underlie this process. So for most problems, this will not be a deterministic sequence. Okay, so if it was deterministic, we could essentially plan ahead everything that would happen. So we could say, oh, I'm currently in state 0, then let me execute a certain action. I know what reward I'm going to get, and I know what state I would get into. And then I could decide already what is going to be the next action and so on. And this would make the problem a lot simpler. Not necessarily perfectly solvable, but a lot simpler. The reality is that in practice, even if we know what state the environment is in and we execute an action, we're not certain what reward we're going to get, and we're not sure what is going to be the next state of the environment. So we're going to model this using the notion of a stochastic process. Okay, so here there's lots of processes that we could use to model this. Now, what tends to happen in practice is that most processes have some structure. They're not completely arbitrary. And what I mean by this is that the laws of the process often do not change over time. Okay, so the process is essentially the dynamics of how states, actions, and rewards would evolve. But then here, I'm going to claim that in many situations, in many problems, the laws of the process do not change over time. And then it's also the case that for many problems, there's a short history that is sufficient to predict what is going to happen next in the future. And here when I say predict, I don't mean necessarily in a deterministic fashion. So it could be a probabilistic prediction, okay? But often there's a history that we can keep short and might be sufficient to predict the future. So as a concrete example, what if we look at weather prediction? So here, when we make predictions for the weather, there's some model that is used. So there are various models about, I guess, how humidity, wind, temperature, and so on will influence each other in various locations. But that model is the same model that is used every day. Okay, so when I said that the laws of the process do not change, right? So for weather prediction, obviously the weather changes every day, but the model that we use to make predictions typically is going to be the same. And then we can assume that it's not just our model that we've constructed, but that really nature uses some underlying process some underlying laws that do not change over time. Okay, so that's an assumption. It's not always the case, but this will be a useful assumption. Then the weather measurements from the past few days are often sufficient to predict what is going to happen in the near future, right? So if we want to predict the weather tomorrow, the day after, and so on, obviously the measurements that we have right now are important. Maybe we can look back a little bit in the past, see how those measurements have evolved in the past few hours, maybe in the past few days, but we don't need to look back a month ago, right? So this is unlikely to help us in any way. So in general, for weather prediction, you can just look at measurements from a short history. Okay, so now we are ready to formalize a stochastic process. And here, to keep things simple, let me just consider states. So we talked about states, actions, and rewards. Now, for the purpose of defining a process here, I'm going to look at a process that corresponds just to the sequence of states. We're going to make this more general in the coming lectures. We'll come back and add actions and rewards again, but for now, let's just restrict ourselves to states. So a stochastic process with respect to states is going to have perhaps a set that defines what are the possible states, and then there's going to be some dynamics that in general we can express by some conditional distribution over the current state given the past states. Okay, so this is a general way of defining a stochastic process. And graphically, you can think of it this way, that this is the state of the environment at time step 0. This is at time step 1, time step 2, and so on. And now, if I want to predict what is going to be the state of the environment at time step 4, then it depends on the state of the environment at time step 3, as well as time step 2, time step 1, and time step 0. So at least in the most general fashion, right? So it might depend on everything that happened before. So here we can express a conditional distribution that will have the state at time step t depend on all the previous states of the environment. Any questions regarding this? Okay, good. So, and let me just point out that in this graph, the circles are random variables here. And then so I'm really just expressing that each random variable has a dependency on other random variables with those arcs. So this would be essentially a probabilistic graphical model, like a Bayesian network. But if you're not familiar with this, right, like the key is just that there's some dependency between these variables, and this is expressed by the dynamics here. Okay, so now there's a problem with the previous picture, because if I have a process that is very long, right, then this conditional distribution that tells me what might be the state at time step t could depend on a number of states before that could be very long, very large, right? And then expressing this type of conditional distribution will be intractable, and it might have to be infinitely large. Okay, so here, if the process was infinitely long and every state was depending on everything that happened before, then I could not express this. Okay, so that's a first problem. So the solution to this is going to be to make two assumptions. First, we're going to assume that a process is stationary, and second, that the process satisfies the Markovian property. Okay, so here what I mean by a stationary process is that the dynamics do not change over time. So we've seen this already in the context of weather prediction. And then the second one, the Markovian assumption, is going to be that the current state depends only on a finite history of past states. So this was this idea that there's a short history that is sufficient. Okay, so these are two very important assumptions that are very common and that we're going to make use as part of our definitions. Yeah?
Doesn't the Markov property usually assume it only depends on the previous state, like the one previous state?
Yeah, good question. Yeah, so does the Markov property assume that it depends only on the previous state? So in some definitions that's correct, but we're going to see that there's a more general definition where there's a notion of k-order Markov processes where it might depend on k previous states. Okay. In fact, okay, here we go. So k-order Markov processes. So here we're going to assume that the last k states are sufficient. So what it means is that if we have k is equal to 1, we're going to have a first order Markov process where the distribution can be rewritten as a simpler expression that depends only on st minus 1. Okay? And we're doing this again because in terms of representation, in terms of computation, it would be intractable otherwise to keep everything into account. So we'll typically want to shorten this. And then the most succinct thing would be just to consider the last state. Okay, so the graph now changes to essentially just a sequence of states with one arrow that just connects one state to the previous one. But now if we want to consider more than just the previous state, maybe the last two states, then we could have a second order Markov process, and then we would have every state that depends on the previous one and the second last one, right? So this would be the picture. Yeah, so in general, when people talk about Markov processes, they usually mean a first order Markov process, but more generally, it can mean as well a k-order Markov process where it depends on the last k states. Okay. So a Markov process, when it is first order, it means that we have this property where for any time step t, we're going to have a conditional distribution that just depends on the previous time step. And then in addition, if we make the assumption that the process is stationary, it means that this conditional distribution is going to be the same regardless of which time step we consider. Okay, so in this expression, you see the right-hand side depends on t prime and the right-hand side on t. Right? So here I'm essentially equating these two conditional distributions for two different time steps, and I'm saying that it will be the same for any time step. So that means it's stationary. So this is a little bit counterintuitive because obviously the process is changing, at least the states are changing, but the dynamics of the process won't be changing. So we're going to assume that they remain the same. Okay, so the advantage of this is that now we can specify an entire process with a single concise conditional distribution. We just need the property of S prime given S. Yes? Oh, where's t prime in the stationary process? So it's right here. Oh. How are they defined? So these would be two. How are they different? Yeah, so they will correspond to different time steps. So I might have time step 0, 1, 2, 3, 4, 5, etc. Right? So every integer could be a different time step. So t and t prime could correspond to any integer here, any positive integer.
So you're saying that any two consecutive states are same, right? How
That's right. So any pair of consecutive states are going to be related by a conditional distribution that is the same regardless of which time step we're at. Yeah. Okay. So as a concrete example, so if we consider robotic control, so let's say that here we've got a robotic arm, we're controlling the different articulation in the fingers so that we can grasp things and so on. And so for every joint, we might want to model as the state the XYZ coordinate of the joint plus the angle. Okay? And then the dynamics, we could assume that the motion of the joint is going to be constant, and this would satisfy our condition here for a stationary process. But obviously, this might not hold because in practice, I mean, velocity or motion is not going to be constant, so there might be some acceleration. And then we'll see how we can deal with this. As another example, so here we could consider an inventory management problem. So what it means is that perhaps the state is defined by the inventory level, and then we've got some dynamics. So this corresponds to how the inventory level change over time. So the demand for different widgets is going to be assumed to be constant but stochastic. And this might not always hold, but it's an assumption that we're making. Okay, so when these assumptions do not hold, what can we do? So it turns out that we can often add new state components to our description to make those assumptions closer to holding. So if, like often those assumptions are not going to hold simply because we don't have enough features in our state representation. So in the case of robotics, if you've got just position, right, and now you assume that velocity is constant, but in practice it's typically not, so velocity will vary because of acceleration, then what you can do is simply add velocity to the state representation, and now instead make the assumption that acceleration is the one that is constant. Okay? Now obviously this might not hold either, so you might say, well, what if acceleration varies? So then what we can do is simply add acceleration to the state description and keep on going. Okay? And then I guess at the end the question is, well, where do we stop? So in theory we might not be able to stop, but concretely you see here this is similar to like when you take a function and then you examine the Taylor series approximation, right? So this would correspond to I guess the position, then after that first derivative, then acceleration would be second derivative, and so on. So you can get a closer and closer approximation through the Taylor series expansion. And then the idea is the same here. So for your process, you might get something that is closer and closer to satisfying the Markovian and stationary assumption simply by adding more and more components. Yeah, so the problem with what I just described is that now when we augment the state description, then obviously the computational complexity will increase. So here, then, the key will become, can we find the smallest state description that still satisfies Markovianness and stationarity? So this is not something easy to come up with. It often requires some domain knowledge, but otherwise this would be the ideal to essentially come up with that smallest state description. Okay, let's say that now we have a process that is Markovian and that is also stationary. Now what can we do with this, right? So an interesting question will be, can we make some predictions? In other words, can we do inference to predict what will be the value of some future state? And the reason why this is important is because in a Markov decision process, and more generally in reinforcement learning, the goal is going to be to select actions that will influence future states and hopefully get us into some states that have high reward. So if we can predict what the future states are going to be, then perhaps we can select some good actions. If we can't predict what the future states are going to be, then it's going to be much harder to select the actions. So a core of Markov decision processes and reinforcement learning is going to be this ability to make some predictions, and it's based on that we're going to select our actions. Okay, so here, yeah, we'd like to perhaps predict an action k times steps into the future. What this means computationally is that we can simply take advantage of the chain rule in probability theory to expand this into a product where we sum out all the intermediate states. Okay? And then if we have discrete states, so finitely many states, then we can represent the conditional distribution as a matrix. And here I'm going to use the letter T to indicate that this is a transition matrix. And what we're really doing in this product is we're essentially taking the product of that matrix by itself k times. Okay? And the reason why it's t to the power of k is because we assume that the process is stationary. Therefore, at every time step, we have the same conditional distribution and therefore the same transition matrix T, right? So if you're looking k steps into the future, then you would multiply the transition matrix by itself k times, and that's why it's T to the k. Now the complexity of doing this is going to be k times s cubed, because whenever we multiply some matrices together, so if I've got a matrix that is of size s, right? So S by S, then you multiply two matrices together, then it takes cubic time with respect to the dimensionality of that matrix. Okay, so that would be the complexity. And then in general, this will be some core operations that we'll want to do to be able to predict future states. Okay, any questions regarding this? Yes?
Why we need a matrix other than maybe just a scalar?
So, okay, here, I guess in the next few slides, I will, I guess in the next set of slides, I will make use of some matrix notation, and then when we analyze some properties of Markov decision processes, then it will be much simpler. So I guess I'm starting to introduce this by saying that, okay, we can think of this as a transition matrix, and then really when I take this product, all I'm doing is really multiplying the matrix by itself k times. Okay? Yeah.
And where does this summation go? Because we have only the multiplication.
Oh, okay. The summation is implicit because whenever we multiply two matrices together, it's not just a pure product. You're actually multiplying some entries together and summing them together, right? So there is an implicit summation each time you multiply two matrices. So this really captures not just the product, but also the summations. Yes. Okay. Yes.
What are the elements of T? Is it the probability going from each state to another state?
Yeah, so this would give us the probability of going from some state at time step t to any other state at time step t plus k. Yeah. Okay, so this is good. So we can make some predictions. However, predictions by themselves are not very useful, right? So that's not the goal. Whenever we make a prediction, it's because we want to use that prediction to select some action, make some decision, okay? And this is going to lead to the problem of decision making, and this is where we're going to need a model that's more comprehensive that takes into account as well actions, and this will lead to Markov decision processes. Okay.